Okay, so this problem asks us to carefully describe the structure of all simple Z modules. So first, let's recall that Z modules can be identified with and are really the same thing as abelian groups. Um, so like more formally, there's an isomorphism of categories between the category of Z modules and the category of abelian groups. Basically, uh, from Z module to a abelian group, um, you just sort of forget the scalar multiplication, and in the other direction, you define the multiplication as repeated addition. Um, so Z modules are really just the same thing as abelian groups, and so we need only to classify all simple abelian groups. And now recall that what does simple mean? Well, simple means that you have no uh, non-trivial proper normal subgroups. Um, so recall that a simple group is one whose only normal subgroups are 0 and itself. So just 0 just denoting the identity, the trivial subgroup and the improper subgroup itself. Um, so the next thing to recall is that uh, every subgroup of an abelian group is normal, of course. So what we really need here is um, to say what groups have no non-trivial proper subgroups at all. Okay, so um, aside from the trivial group consisting of just an identity element, let's suppose that we have uh, uh, at least two elements. So let G be a non-trivial um, simple abelian group. We want to describe the structure of G. So, all right, so let X be any non-identity element, since we're assuming G is non-trivial, we have one. Um, and uh, so remember, we're interested in um, so groups that have no non-trivial subgroups. So let's consider the cyclic subgroup generated by X, which we denote like this, and which we know is a subgroup of G. Okay, well, this is a simple group. So, and cyclic groups are abelian. So we cannot have uh in a simple abelian group, we can't have any non-trivial proper subgroups. But uh this cyclic subgroup generated by X cannot just be the identity element because X is not the identity element. So it must be the case. It must be the case that this is actually the whole group G. So G is cyclic in particular because it's equal to a cyclic subgroup. So, um, well, there are two cases, right? Cyclic groups come in two flavors. The finite cyclic groups are of the form Z mod PZ for P prime. And then every infinite cyclic group is isomorphic to Z, the group of integers. Um, but uh, G cannot be isomorphic to Z since Z has non-trivial proper subgroups. Such as 2Z or NZ for any N. So G is isomorphic to Z mod PZ for some prime P. And thus we recover the structure of all the uh, simple Z modules or the simple abelian groups. In particular, all the simple Z modules are isomorphic to the group Z mod PZ, where P is prime. So the cyclic groups of prime order, finite prime order.